Good morning. So we'll be starting this session, and it's just wonderful to be here again with the Ecsite family as we have the pleasure of sponsoring the Kavli Foundation keynote lecture. And I'd like to thank Ecsite President Herbert Munder for his very warm welcome yesterday, as well the case that he and Catherine French and the other speakers articulated beautifully regarding the importance of the work that you all do cannot be overstated. You are a bridge between science and society, between scientists and other citizens. Now, the mission of the Kavli Foundation is to advance science for the benefit of humanity, to promote public understanding of scientific research, and to support scientists and their work. Our founder, Fred Kavli, a Norwegian immigrant to the United States, focused our scientific support on investigations of the smallest, the biggest, and the most complex at the frontiers of science. Now, the Foundation's mission is implemented through an international program of 20 endowed research institutes at major universities around the world, including here in Europe, symposia and other initiatives in the fields of nanoscience, astrophysics, theoretical physics, and neuroscience. And the Kavli Foundation is also a founding partner, along with Norway, of the $1 Million Kavli Prizes, which recognize scientists for their seminal work in areas of astrophysics, nanoscience, and neuroscience. And their purpose is also to promote the public understanding of scientists and their work. And I'll digress for a minute to mention that the 2018 Kavli Prizes were just announced last week. And I'm happy to say that the majority of winners were Europeans, and as well, the majority of winners this year were women. So my role, and that of my colleague Brooke Smith, who is also here from the Kavli Foundation, is to specifically focus on the second part of our mission, to the support of the connection between citizens and scientists and their work. Now, our strategy is to strengthen this field and to draw attention to the critical role that you all play in connecting science to the public. So today, it's my distinct pleasure to help sponsor this Ecsite keynote. The speaker, in 1 minute, you'll meet James Beacham. He's a particle physicist right here at CERN, and he also has a degree in film. Now, he calls himself a full-time physicist who is drawn to answering the biggest and the smallest things in the universe, drawn to extremes. He tells me that he focuses on the edges of what we know. And his interest in film was specifically in how to illuminate complexity to make it understandable. Now, he sees himself as a better scientist if and when he interacts with people. So now I have the pleasure to welcome James Beacham to interact with us as he brings us to the edges of the smallest, the biggest, and the complex in our world. Thank you very much.
Thank you very much. Can I be heard? Can I be heard? Okay, this is good. So yes, thank you very much. I grew up in southern Utah, and this is the home of vibrant red and black rocks, hot August nights and clear skies, and these are perfect conditions for stargazing. And I remember one night as a kid, my science teacher had invited a bunch of us students to drive out of town, away from the city lights and up to the side of a high sandstone ridge. And as we reached the top, our teacher turned off the van's headlights, and we slowly arrived at a clearing. In the distance, we could just barely see a dim red glow, and as we came closer, the glow turned into a group of telescopes and a bunch of people that were fiddling with them. We were there to photograph the rings of Saturn. our teacher had arranged with some of his amateur astronomer friends to let us do this special assignment where we'd all get a chance to learn a bit about how telescopes work and how to take photos through them. And we'd then choose our own subject in the night sky, take a photo, and the astronomers would print it for us, and then we would talk about them back at school. So everyone was particularly excited because our teacher had told us that this was a particularly good night to see Saturn's rings. And there were about 5 or 6 telescopes for about twice as many students. And although people are usually pretty calm and quiet at star parties, that's what these are typically referred to as, this one was a bit loud since it featured a group of boisterous, inquisitive kids. Where is it? Can I look? Where is Saturn now? Can I take my photo yet? Why can't I see Saturn with my eyes? Can we take a photo of a black hole? Is that Saturn? It's kind of small. Why is it bigger in this telescope? Oh, cool. I can see Saturn's rings, kind of. Whoa, I read that Saturn's rings are made of ice and rock. Oh, I bumped it and I can't see it anymore. Is it my turn yet? How far away is Saturn? My dad says that the stars are a mile away. Can I take my photo now? I took my photo. Can I look at Saturn through all of the telescopes? I can see it through all of them. Cool. Hey, Melody, what are you doing? We were all boisterous, inquisitive boys, except for Melody. Melody was the only girl in the group and an indigenous Native American from a local tribe. I don't remember if she was Paiute or Navajo. She wasn't as loud as the boys in the group, and after she'd had her first look through the telescopes when we were trying to find Saturn, she then stood toward the back as the others clamored to use them. I wasn't as interested in yelling as the other guys were, so I stood off to the side with her, and we talked about school, in the night sky, and how her grandma had a different name for the mountain we were on than the one that our teacher had used. As everyone else was trying to get in on the telescopes and take their photo of Saturn, we noticed that there was one telescope and one camera rig that was a bit older, so no one was using it. The astronomers told us that the other scopes were better for Saturn, so it was just sitting there. So Melody and I were standing around, and we decided to play with it a little bit. I pointed it in the direction of Saturn, but couldn't really see much. We could see some point stars and other small sources, but otherwise there didn't seem to be much there. So after a bit of messing around, I left Melody to go finally wait to take my photo of Saturn. But then, after a longer while, somebody looked over and said, "Hey, Melody, what are you doing?" Melody had this older telescope and camera and had pointed it in totally the opposite direction from where everyone else was looking. "Hey, Melody, Saturn is over this way. Melody, there's nothing over there. Can I look? I don't see anything. There's nothing there but dark sky." But Melody just said, "I'm just looking around." And one of the astronomers said, "Feel free to do so, and if you'd like to come and take a photo of Saturn afterward, please join us in a bit." But the guys made it clear that she was wasting her time. There's nothing there but smaller stars. Saturn is over here. The next week, one of the astronomers brought our photos into class. We were all eager to look at them, so he put them up on an easel, and we looked at them one by one. The Saturn photos were nice, John's and Jared's and Bob's, and they were a good first attempt at astrophotography, the guy said. They were pretty big images. They were mostly a blank field and a relatively small blob somewhere on the image that was a bit blurry, but that definitely showed the characteristic ball plus waistband of Saturn. He got to the last Saturn photo and then turned the page to the final photo, which looked totally and completely different from the others. This image was filled with objects and structures, points of light, different brightnesses, shapes, sizes, several clearly stars, many much bigger and almost spiral-looking, most likely galaxies, with a series of very bright stars that appeared as huge lit crosses scattered throughout the image. And there was a kind of gauzy structure over part of the image, maybe a mistake, but maybe a nebula-looking mist. It was spectacular compared to the others. And it had the name Melody attached to it. The guy said that Melody had taken several long exposure shots with the other telescope, and he'd combined a couple of them to make this image. Melody had found structure that was right there, but that we couldn't see immediately with our eyes. And the guys were very impressed. "Wow, cool, is that a black hole?" And one of the guys said, "Melody, how did you do that?" Melody shrugged and said, "I looked where no one else was looking." Melody looked where no one else was looking and found a hidden realm, a secret behind-the-scenes structure, something that was there all along, the finding of which totally changed our perception of the universe, at least in our class, and our perception of what's possible. There was a reason Melody and I were friends, because for better or for worse, this is a principle that I have tried to follow my whole life. Look where no one else is looking. Look at what's right in front of us in a different way to hopefully find hidden realms and structures underneath. And science, for me, as a little kid, was never a label and never really something that I felt like I would become or not become. I was sort of a library guy, so I spent a lot of time reading books, going to science museums, messing with electromagnets and chemistry sets, and after enough investigation, it became clear that science was just the word that we applied. Was just the word that we applied to the self-evidently best way we know of for asking and answering questions about the world. I was indeed that kid who always wanted to know more and who never accepted "that's just the way it is" as an answer. Maybe I wasn't the loudest question asker at first, but I always went in search of a better answer, and science was obviously the most powerful and impressive method we had for understanding the world around us. So naturally, when I got to university, I chose a major course of study in filmmaking. I'd also always been obsessed with cinema as a means of examining complex ideas. Social, psychological, political, and my enthusiasms at that moment were squarely in the realm of experimental cinema, so it seemed natural to pursue it. But I remember that on film sets, I was simultaneously reading physics books during breaks, and I finally decided I was doing myself a disservice if I didn't formally study physics. I had never lost this obsession with understanding the basic rules of nature, of wondering about the hidden structures of the physics world around us. So I ended up completing a second degree, a double major in physics and math, before making my way to a PhD program in physics as well. And if you keep asking these questions about the invisible structures of the world, the why and how behind the why and how, eventually you find yourself in particle physics. And if in particle physics you are naturally drawn to the very edges of human knowledge, the very boundaries of scientific inquiry, you eventually find yourself at CERN. I'm now a particle physicist right up the road at the Large Hadron Collider, the biggest science experiment ever mounted, where the entire name of the game is to explore nature at its smallest possible scales, looking for hidden structures, hidden rules that govern the world around us, to explain some of the biggest open questions and mysteries of the universe, such as, there we go. What is 95% of the universe made of? Why is gravity so extremely weak compared to the other forces of nature? What really happened just after the moment of the Big Bang 14 billion years ago? And do we live in a multiverse? Kind of boring questions, right? So, and I have the extreme honor of speaking to you right now in 2018 because particle physics is right on the cusp of a revolution. Our universe seems a lot weirder than it did even 10 years ago, and we don't know how to explain this weirdness yet. A reminder, yes, so the Large Hadron Collider is a 27-kilometer tunnel on the border of France and Switzerland, right here, buried about 100 meters underground. And in this tunnel, we use superconducting magnets colder than outer space to accelerate protons, you're made of protons, to almost the speed of light and the highest energy that humans have ever used in a collider experiment. There are two beams of protons that zoom next to each other in opposite directions around the ring, and then at 4 points on the ring, the beams are crossed, and the protons slam into each other millions of times a second. In the place where you collide these protons, you'd better build a large detector, because quantum field theory wonderfulness is going to happen. And by large, I mean very large, like the one that I work on, which is called Atlas. Atlas is 6 stories high, 46 meters long, and it's like a gigantic 100-megapixel camera that takes 3-dimensional photos 40 million times a second. And this is some lucky guy that got to stand there as they were constructing the thing, pulling in the inner part of the detector. Hopefully wasn't standing there as they pulled the rest of that in. That would be very sad. The design, and this is, so it takes 3D photos 40 million times a second. second. And we do this for weeks and months and years. And this is how we collect a record of the outgoing debris from these collisions to search for new, undiscovered particles that could be answers to these big, open questions of physics. The design and construction of the LHC took decades of work by thousands of physicists from around the globe, and non-physicists as well. An atlas requires also thousands of people to operate and to maintain and to analyze the resulting hundreds of petabytes of raw data to look for evidence of new particles. Everything about the LHC is big. Big collaborations, big experimental size, the very definition of big data, which is only appropriate because what we're studying are things that are so small that live for such a small amount of time that you'll never interact with them directly. And this is a slightly embellished version of one of those snapshots of an individual proton collision called an event display. And this is the sort of wild thing that I look at all day long. What you're seeing is a circular cross-section of where the two proton beams have slammed into each other. Something happened, possibly a new particle was created, but overwhelmingly probably not. And then a bunch of particles flew out from the interaction point and hit our detector. And we measure everything about these outgoing particles, at which angles they hit the detector, the curviness of their trajectories, the amount of energy they leave behind, and we perform heroic feats of complex data analysis to determine if what we're seeing is evidence of a new particle, evidence of some new hidden realm, or evidence of what we'd expect in the absence of a new particle. Signal versus background, the old story. And even though you're all science professionals, even though you're all science professionals, it's entirely possible that not all of you are physicists, and it's entirely possible that the point of all of this research is not 100% clear. So I often like to remind myself that everything we're doing here at the LHC, at the end of the day, comes down to a sliced bagel. So I take a bagel and cut it in half. Then I cut the half in half and keep going. How far can you go? Eventually get to a molecule, right? Can I cut a molecule? Of course you can. Cut it into atoms. Can I cut an atom? Yes, an atom is made of some stuff like a nucleus and some electrons going around the outside. Can I cut those pieces? Can I cut an electron? As far as we know, no. An electron is a point particle that has no volume, no spatial extent. It's entirely possible, though, that there's structure inside an electron, but our current ability to probe at such distance scales is impossible for us to tell. So to our current knowledge, an electron is a point particle. But what about a proton? Can I cut a proton? Yes. It turns out that there's stuff inside of a proton, some particles called quarks held together by gluons. I didn't come up with that name, some joker came up with the name. But can I cut a quark? As far as I know, no. So you see that when you ask a seemingly simple question, how small can I cut anything? You're secretly asking a much more profound question. What was holding anything together to begin with? It turns out that particles interact via the exchange of other types of particles, vector gauge bosons, or force-carrying particles. We had dinner last night at an ice hockey rink, so imagine you and your friend are standing facing each other on an ice rink, and you're holding a huge, heavy rock. When you throw the rock to your friend, you're going to glide backwards on the ice. And when she catches the rock, she's going to glide backwards as well. So you two have exchanged a force-carrying particle, and this is how stuff happens at the level of particles. And the history of particle physics throughout the 19th, 20th, and 21st century was a matter of asking these questions. How small can I cut? How is anything being held together in the first place? In a controlled way, and asking the questions based on an increasingly well-understood theoretical and mathematical framework and answering them in a large number of experiments. And this wonderful interplay between theory and experiment eventually resulted in what is known as the standard model of particle physics, and which is essentially a list of all the known elementary particles and the ways that they interact. And the last remaining piece of this standard model that was predicted was something called the Higgs boson. Who's heard of the Higgs boson? All right, that's good. A sea of hands. I like it. This is an extremely unique particle and a very weird particle compared to these others. And as you know, the Higgs was finally discovered here at the LHC in 2012. Excuse me. Which was an amazing and colossal discovery by my colleagues and I, hooray. And of course, 2 white males received the Nobel Prize. What else is new? And it really is a fantastic discovery, and it's our newest and shiniest toy, and we'll be studying it for many decades. But there's a catch. Two catches, in fact. The first catch is that although the existence of this particle, the Higgs, was predicted by the standard model, its mass was not. And the place where we found the Higgs is a bit weird. And the circumstances around it make us start to think that our universe is a bit weird. The second catch is, although the standard model is fantastically successful and frankly beautiful and elegant theory, it's arguably the greatest intellectual achievement of humankind. Of course, I can pat ourselves on the back for that. We know for a fact that it's incomplete. We know this. We know for a fact that it cannot be the complete description of nature at all of its fundamental scales. One simple demonstration of that. Remember I said that standard model is a list of all the known particles, matter particles, and the ways that they interact via exchange of force-carrying particles, right? Well, what's a force that is all around us all the time? Gravity. Guess what? Gravity is not in the standard model. We know that gravity exists, I just showed you. So this demonstrates to us for a fact that this and for a few other reasons we know that there must be new physics. We know that there must be new particles beyond the standard model. And finding them, this is the hard part. It took almost 50 years from the prediction of the Higgs boson to its discovery. Why did it take so long? It essentially comes down to, Einstein. Everybody loves Einstein. Einstein's most famous equation is E equals mc squared. And it's essentially a statement that energy can't be created or destroyed, but it can be moved around. And for particles, it can be stuck into a property called mass. Mass at the particle level is not the same as our colloquial use of massive, like, hey, look at that massive airplane. Remember, these are point particles. Mass is a property of a particle, a number put there by nature, like charge or spin. So nature controls this part. The part that we as humans can control is this part, the E part. Think about it. If nature has a particle with a mass m that's all the way up here, and we as a species have only ever built, I'll get it this way, an experiment with an energy that's down here, we'll never be able to find it, discover it, and measure that particle, the properties of the particle. And this is why the Higgs was hard to find. We didn't know where it would be in mass, so we had to sweep out higher and higher energies at bigger experiments until we found it. And we finally did in proton collisions at the Large Hadron Collider. But wait, think about that. Dig deeper. Probe deeper into the hidden realm. What do I mean by that? We collided two protons, and a Higgs boson was hiding inside the proton, and the collision popped the Higgs out of the proton, or something else? What's really going on inside of a proton collision? What's really going on? Oh, TeV. If you see this TeV thing, it's more or less just a measure of energy, and more of that is better. Tera electron volts, because we're all scientists here. What's really going on inside of a proton collision? What's really going on is when two protons collide is that the two protons get close enough so that the constituent particles inside, the quarks and gluons, can feel each other. When they get close enough, two of the quarks, for example, can be pulled out of the proton. And those two quarks are the things that collide. And this is what we really want. Due to the nature of the strong force, that gluon thing, we can't build an individual quark collider. So in lieu of that, we build a proton collider. And we tried to get the protons really close to each other. And this is important because when the two quarks, which are point particles, collide, this is when new particles can be created. Because, using the example of you and your friend on the ice skating rink, if you were really two particles, you would have another option. Not only could you exchange the heavy rock, the force-carrying particle, but you and your friend could smack together on the ice and become the rock. Okay, perhaps a different metaphor. Particle collisions are not like car collisions. They have different rules. When two particles collide at almost the speed of light, the quantum world takes over. And in the quantum world, two particles can briefly cease to exist and a new particle is created in their place. And that particle lives for a tiny fraction of a second before splitting into other particles that hit our detector. Imagine a car collision where the two cars vanish upon impact, a bicycle appears in their place, and then that bicycle explodes into two skateboards, which hit our detector. Hopefully not literally, don't hit our detector with a skateboard, that's very, very bad. So, and we use diagrams like these, called Feynman diagrams. Feynman diagrams, there we go. Feynman diagrams to give a pictorial representation of these collisions. So space is on the y-axis, time is on the x-axis. So you can see at some point in time, two quarks are far apart, they get closer together, they annihilate, and a Z boson is created in their place. And that Z boson then decays into two muons. But this seems bizarre. Come on, you have to admit, that seems totally bizarre. We started with two quarks and it ended up with two muons. This is bizarre but totally logical because we remember that quantum field theory doesn't care about the names we give to the particles. It only cares about, remember your high school physics, conserved quantities like energy, momentum, charge, spin, etc., which are carried by these point particles. So long as you satisfy these conservation laws, you can put whatever you want there. And that middle part, that's the part we care about. Because this could be something like the Z boson, which we know and love and was discovered many decades ago, or it could be something like the Higgs boson, or it could be something completely new, a totally revolutionary particle that could be waiting for us to discover, like a hyperdimensional graviton at higher energies. And this is where the Large Hadron Collider comes in. Prior to the LHC turning on, we had no idea if the Higgs boson existed, but we were hoping to find it. But the existence of the Higgs was just one open question for physics. The LHC was such a huge jump in energy from prior experiments that we had the possibility of a wide range of discoveries, and we still do have a possibility of a wide range of discoveries. So when we first turned on the LHC at 7 and 8 TeV, that measure of energy that I mentioned earlier, at the time, the highest energy ever, and pow, where's that pow? There we go, Higgs boson. When we got up to 8 TeV, that's where we found, 7 and 8 TeV, that's where we found the Higgs boson. It was a record at the time. But the LHC was designed to go higher. So in 2015, after a couple of years of maintenance, the LHC was being prepared to go higher to 13 TeV. And this was go time. So on June 3rd, 2015, many of us gathered in the control room of the Atlas experiment, gazing into the distance like Norse explorers, and the mood was electric with anticipation. And when we finally saw the first collisions at 13 TeV, it was an amazing moment. Champagne and celebration. This was the highest energy humanity had ever achieved in the collider experiment, and we had no idea what sort of discoveries we would find in this data. And I can tell you now, in 2018, that after 3 years of our first look at 13 TeV, we so far found nothing else. So why am I smiling? Because this is the exciting part, both exciting and puzzling. It's puzzling because we had some degree of expectation that there would be new particles beyond the Higgs, just well within the reach of 13 TeV, particles to help explain these other huge open questions of physics. And it's exciting because the lack of a discovery can eventually yield radical paradigm shifts, as you know quite well, because it makes it seem, in this case, like our universe doesn't make any sense. Two examples, and they're related. Dark matter. So everybody loves Hubble photos. Take your favorite Hubble photograph of a spiral galaxy and count up all the stuff that you can see, all the stars. Then that gives you a measure of the amount of matter that's in that galaxy, right? And then you can just take your favorite book about gravitation, your favorite math book that has the equation that says how fast a star should be moving as a function of how far away from the center of the galaxy it is. It's just a number, it's just an equation. You can pull it out of the book, put it right in there. It tells you exactly how fast it should be moving. Then go out and measure how fast it's moving. It's totally off from the prediction. In fact, it's so far off that it makes you think that something has got to be up. So one of two things is wrong. Either gravity is wrong, it's probably not or there has to be more stuff there than what we can see with our eyes. And if it's not light, it's dark. That's where the dark matter part comes from. And we used to have, and the key point with dark matter is that we used to have a lot of hints and expectations as to where dark matter should show up, but those hints aren't panning out. Dark matter is still a mystery. But because dark matter hasn't shown up yet where we expected it to, a few people are already investigating alternatives to the idea that dark matter is a particle, because that's basically behind the scenes in all of that assumption. There's some extra particle that can explain what dark matter is, or some set of particles. But because of the lack of discovery so far, this starts people to take a little bit more seriously things that could be, in principle, radical paradigm shifts. So some of these alternatives to dark matter as a particle ideas are not so reasonable ideas in the sense that they suggest modifications of gravity itself that simply don't match with most of our observations. But some of them are intriguing but not yet so well-established ideas, such as the idea that dark matter is an unnecessary hypothesis because gravity itself is not a fundamental interaction, but is an emergent property of a holographic universe encoded in qubits, and I'd be lying if I said I was the super expert on this idea and this conjecture. But my colleague Eric Verlinde is onto an intriguing idea which is being developed now, and if it results in some predictions that satisfy experimental tests and do better than our standard dark matter ideas, then we could be on the cusp of a revolution. The second example is related to the Higgs boson itself. Recall that I said that the Higgs boson mass isn't predicted by the standard model. And in fact, it's worse than that. There's nothing in the theory to prevent the Higgs boson mass from being something gigantically huge, something like 10 to the power 16 TeV. 10 to the power 16 TeV, what is that? And this is well outside of the range of the LHC, but we found it down here at around 0.1 TeV. This is puzzling. One way to solve this puzzle is by postulating the existence of essentially an extra copy of the standard model particles under a framework known as supersymmetry. And I don't have time to dig into the details here. Many of you probably already know some of these details in this short amount of time, but suffice it to say that if we had found some supersymmetry particles just around the corner in the jump from 8 to 13 TeV, these particles would have, in essence, provided a very good explanation as to why the Higgs boson mass is what we observe. But we haven't found these supersymmetry particles yet. And this is a major puzzle because it makes it hard to understand why the Higgs mass is what it is. Why would the Higgs be sitting right where it is? What could be the reason? What could be the underlying structure, the hidden rules governing our universe's Higgs mass? Well, one explanation is a bit wild. Recall that nature loves statistical distributions. Hopefully you recall that. The average resting heart rate of an adult male, for example, will be distributed as a Gaussian or a normal distribution. And if you stand on the street corner, a frequency with which cars will pass you will follow some kind of a boson distribution. So the universe, our universe, loves statistical distributions. So what if our Higgs mass is simply one of an almost infinite number of possible Higgs masses chosen from a probability distribution that governs the values assigned to those universes in a multiverse? In this case, because our Higgs mass was just right to allow atoms to form and stars and planets to come into being and eventually for us to be here having this conference, our Higgs mass is appropriate for a stable universe. And for almost all of the others, the value would have been something leading to an unstable universe that didn't even have a chance to expand, or where it expanded but atomic structures never formed. The lack of supersymmetry at 13 TeV at the LHC is in no sense evidence of a multiverse, but it's an example of how the lack of a somewhat expected result can spur radical new thinking and compel us to take more seriously ideas that previously would have been squarely in the realm of science fiction. And to be clear, we'll be taking data at the LHC for many more years, so everything I'm saying could be totally rendered moot, like, next year. and with many possible discoveries therein. But if the LHC goes for the duration of its research program and verifies the standard model, that is, only discovers a Higgs and nothing else, what happens? We'll do the only logically necessary thing we can. We build a bigger collider. We go to higher energies. But I heard in the laughs that you just gave, there's a little bit of, funny, but also kind of like, sort of thing. Before we decide to do that, are we really out of hints as to where the new particles discoveries could be hiding? Are we running out of hints? We're running out of hints as to where supersymmetry could be. It could be within the LHC after a lot more data. It's entirely true. And it could be just around the corner at a larger machine, or it could actually be very far away. The one question we'd really like to answer is as follows. Are there new particles at the TeV scale? This was always more or less the background question, but you'll notice that in terms of TeVs, 13 is not that many. To answer this question, we'll have to go big. But is that still good enough? Isn't it hard to justify such a project without at least reasonable expectation as to what we should find? Why should we build bigger colliders based only upon E = mc squared? The reason is that it's always worked in the past. And if we don't look for new discoveries at higher energies, we'll simply never know. If we knew what we were going to find in advance, it wouldn't be an experiment. And throughout the history of particle physics, every time we built a bigger machine, a bigger experiment, we've discovered something new about nature. So here's some examples. Back in the day, in 1897, a lone white male on a tabletop could change everything, and this was J.J. Thomson discovering the electron. Then you go to bigger machines. They started building something called the proton synchrotron. I'm skipping ahead several decades here in the 1950s, and this was a ring that was about 628 meters around. And some lucky guy gets to, I don't know what he's doing. He's collecting rainwater or something. I don't know. Different physics going on back then. And so this is just to give you a sense of the size of the type of experiments that we have designed, my forebears had designed, and what we discovered when we did that. So this was Thomson on a table in Cambridge in the 1890s. He discovered the electron. You go to a bigger machine, the alternating gradient synchrotron in Brookhaven, and this is 800 meters around. And this is where the charm quark was verified to exist. And the charm quark was really important because this was a discovery where it made people take seriously the fact that there's really stuff inside of a proton. And it's not just a nice bookkeeping feature to make the math nice. This was a real discovery. Then you go to a bigger machine, the super proton synchrotron, and this is where the W and Z boson, the Z, the one that I said that we love so much, was discovered at a much bigger machine. And in about a similar size machine, the tevatron, they were colliding a different particle there, the top quark was discovered, and this is the heaviest particle that we know exists. And then, of course, you go up to the big one right now, the Large Hadron Collider at 27 kilometers around, and the Higgs boson. But like I said, the Higgs boson was the last guarantee. That was the last thing to be predicted by the standard model. We don't know where the next physics is going to be. So we have to go as big as possible. The current plans, things that are being discussed right now, will either be something in China, a CEPC planned to be about 50 to 70 kilometers around, probably in the 2040s, something like that. Is that where the new physics could be hiding? It's a big question mark. Or, more likely, it'll be something that'll be somewhere here at CERN. It'll be based at CERN, a future circular collider about 80 to 100 kilometers around. Is that where the new physics is going to be hiding? These projects will teach us untold things about particle physics because it's absolutely true. The new physics could just be right around the corner. But is that really as big as we could possibly go? What if instead, if we really want to definitively answer the question, is there new physics at the TeV scale, why not leapfrog it? Why not instead build a particle collider around the circumference of a great circle of the moon? This would get you up to 11,000 kilometers and up to the I think thousands of PeV scale. This would really definitively answer the question. And the Moon Collider is an excellent example of a possibly revolutionary thing because it's an example of something that just a few years ago would have been insane impossible. But because of big advancements in space travel, robotics, communications, and a large increase in the interest in humans returning to space, for example, establishing a moon base, is now something that is only regular impossible, and regular impossible we can do. Regular impossible is only impossible right up till the moment that someone makes it possible. But a moon collider, a particle physics experiment to definitively answer the question as to whether new particles exist at the TeV scale, and thus to provide more circumstantial evidence that we may live in a multiverse, will only be possible if we as a species collectively agree to think big, to push beyond, and together agree to look where no one else is looking. And why just a particle collider on the moon? If we're going to go big, truly explore the hidden realms of nature, why stop there? How about the Vera Rubin Lunar Science Center? If you don't know who Vera Rubin is, I urge you to look her up. She's one of my heroes. The Vera Rubin Lunar Science Center that would have a particle collider at 30,000 TeV on a great circle around the circumference of the moon, astronomy based on the moon, gravitational wave detectors on the moon, dark matter experiments, precision measurements in low gravity conditions, quantum computing center, an organization, of course, based upon something like the CERN or the ISS models. Let's stop for a second. Whenever I give a presentation about the moon collider idea, and I can say this to you because we're sort of colleagues rather than just me talking to a public audience, and I've presented at a few museums and institutions around the world so far, people love it and are very interested and supportive, especially students and younger thinkers. They love tossing around ideas about how to make it happen. But there always seems to be a but. And even though I'm among scientific and intellectual allies here at Ecsite, I hope I am, a few of you here in this room probably have the following question in your heads. Isn't this absurd? I mean, why would we do this when there's so much hardship and poverty and so many social problems here on Earth? The truth is that the resources exist to both solve all social problems and devote a relatively small portion of them toward boundary-stretching scientific exploration, like a particle collider around the moon, but the current prevalent socioeconomic systems have engendered a world and an attitude that make us think that we have to choose among things like this. The current system and the very small number of extremely wealthy power holders have a vested interest in convincing us that there's no alternative to the current system. That's how hegemonies persist. They aggressively and unrelentingly sell you the fraudulent idea that they're inevitable. But if I, as a physicist, can embrace new ideas and not feel threatened when new information comes forward, new ideas, new paradigm shifts, and not feel threatened when new information comes forward, but embrace and celebrate when new information forces us to change our thinking and conclusions about the nature of the universe, and I guarantee you that if you come up with a theory of physics that incorporates all of our observations of elementary particles and includes dark matter and gravity, a better theory than the Standard Model and general relativity, I guarantee you I will celebrate. We as a society must remain open to the idea that alternate, more equitable systems where everyone wins, we eradicate poverty and explore the mysteries of the universe with a particle collider on the moon do exist, and that we can create them. And even in the current scheme of things, don't ever let anyone tell you that fundamental science projects are some kind of drain on society. Consider it in context. It cost about $8 billion to construct the LHC, and it costs less than $1 billion per year to operate. And the US Department of Energy, I'm just using the US case just because that's where my funding comes from right now, and the US Department of Energy and National Science Foundation contributions to the LHC experiments alone is about $170 million per year, a fraction of their approximately $37.5 billion budget combined. And for comparison, the budgets of the National Endowment of the Arts and Humanities, here we go. This is not working so well. Gave away the thing. Come on. There we go. Arts and humanities are tiny and are currently proposed to be cut and then removed. By contrast, the annual budget for the US military is around $700 billion. And for some private sector examples, Uber is currently valued at $68 billion, Palantir Technologies at around $20 billion, and the total valuation of all privately held companies worth more than $1 billion is $650 billion. If we, as a society, valued scientific curiosity as much as we valued sophisticated government surveillance of the citizenry, providing the state with a more efficient means of aggressively oppressing immigrant populations and undermining strong service sector unions such as those covering taxi drivers, in 50 years, we could build a proton collider around the circumference of the moon and definitively explore the mysteries of gravity, space-time, dark matter, the Higgs boson, and multiverse theory, a realm into which we can only ever just barely stick a toe with the LHC. But we don't currently value things this way. Why not? Why do we repeatedly and consistently capitulate to a way of organizing society that reinforces a value system, the constant pursuit of amoral profit that is antithetical to cutting-edge science for the sake of curiosity? Why do we allow this system to shape people's minds into thinking that science is just science, unless it can be turned into a product for commerce? And maybe those of us in the room don't think that, but a very large number of people in the general populace do. Why do we allow this system to continue to prop up a world where being a scientist is seen as an elitist pursuit, or at least one where this impression is sold to a large number of our fellow humans as a tool of manipulation by powerful and wealthy people? And I adore this concept of the moon collider, because look at just what happened in this room. By thinking big, looking beyond, looking where no one else is looking, simply suggesting building a particle collider around the circumference of the moon as a legitimate possibility has done the exact same thing that's been obsessing me my whole life. It immediately exposes the hidden forces, hidden structures at work, social and psychological structures masquerading as practical, that prevent us from really envisioning a world where scientific curiosity is valued, irrespective of its connection to commercial or practical utility. People say we have no examples of modern societies that are successful, that are arranged in ways different from the current prevalent socioeconomic system, but this is only true on large scales. On small scales, we have many examples, and one of them is right down the road at CERN. Every day, thousands of people from around the globe go to CERN to work for fundamental, boundary-stretching science for peace simply because we want to know more about our universe. We're not going to get rich doing the research we do. The very existence of CERN model is a challenge to the dominant paradigm of organizing societies, because it demonstrates that organizing around different value systems is entirely possible. And these hidden societal structures that prevent us from envisioning big things and reorganizing societies are essentially the same ones that have led to the increase in anti-science sentiment around the world. The increasing mistrust of empiricism as a concept, the erosion of the understanding of the tools and methods of science, and the increasing susceptibility of the populace to manipulation by self-interested people. Physics seems to be on the cusp of a revolution, and it's simultaneously exciting and terrifying because we don't know where this revolution will come from. And in particle physics, it all started in June of 2015. But it's not just physics being on the cusp of a major change. Something else happened in June of 2015. Not too far. Donald Trump announced his candidacy for the US presidency just a few days after we finally achieved the highest collisions ever, the highest energy collisions ever. And after 3 years of institutionalized lying, fake news, racism, misogyny, corruption, anti-science sentiment, and policies, autocratic statements and attitudes both in the US and abroad, it often seems like the world is on the cusp of something too. The world seems to be at a weird point, which could either end in catastrophe, and as adults we must confront this possibility, or the current moment could be the inspiration for true societal change. But true progressive change is only possible if we are smarter about uncovering and fixing the roots of the problems, not just the physical consequences, if we address all the structures around us that lead to a populace that experiences such extreme wealth inequality and that is easily manipulated into racist, sexist, xenophobic, anti-science sentiments. Trump, Marine Le Pen, Viktor Orban, Poland's Law and Justice Party, Rodrigo Duterte, Alternative für Deutschland, and the Austrian Freedom Party, these are all consequences. They're not causes. There are structural issues in society that have led to the world we find ourselves in, when the reputation of science is at a low, and where far too many people are willing to accept confidence as a substitute for evidence. We clearly need new ways to address the problems we face, scientifically, politically, and artistically. to kind of, go in a possibly more positive direction now, sorry. Because for me, something else happened in 2015. I created a project called X-Noise CERN, experimental noise music inside CERN, for one reason. I had a hard time explaining my particle physics research to many of my artist friends. I wanted to run an experiment to not explain, but instead connect with them on an emotional or visceral level with respect to the reason particle physics research like that we do at CERN exists. Part of the reason we have a populace, and I was going to give you this. Part of the reason we have a populace that's more susceptible to being manipulated into anti-science sentiment by powerful people could be that there is a chasm between the biggest advancements in science and our ability to physically experience them. You will never hold a Higgs boson in your hand. You will never stand on a cosmic beach and feel a gravitational wave crash over you. You will never feel this. This leads to a disconnect, this chasm between the real thing we want to know, the previously secret rules by which the universe works, and the thing we can physically experience, collision event displays, cool as they are, reconstructed from electronic blips into nice diagrams, charts and plots with lines on them and numbers and words and papers and articles, all reconstructed by essentially, in particle physics, doing detective work on the decay products of the thing we really want to know about, that new graviton, that new Higgs boson, down in the middle there. Scientists and science enthusiasts understand how this connection is made, how the indirect is scientifically and logically equivalent to the discovery made directly, but there's really a very large amount one must go through to participate fully in our results, in our discoveries, in our vital null results, and null results are awesome, by the way. We find shortcuts to explanation, heuristics that are fundamentally flawed and limited, and we can either live with these flawed and, to the scientist, somewhat unsatisfying heuristics and fine-tune them, or we can investigate new ways to give a sense as to why the research is fascinating. And this was the intention behind the X-Noise CERN project. The crux of the project is juxtapositional, very kind of high concept stuff. We take a boundary-stretching musician, immerse them in the world of the most cutting-edge particle physics, research in human history, operating at the extremes of knowledge, and then inspire them to do some manner of musical improvisation in one of the key, equally boundary-stretching and visually arresting experimental locations here at CERN and make a film of it. This is site-specific experimental noise improv performance. And this first episode with this indie band called Deerhoof made a bit of a splash in the music world, and LHC research appeared in several music press outlets for the first time it ever had. The resulting video immediately leapt into the top 10 most watched things CERN has ever produced, and then an artist friend of mine described the resulting film as Albert Einstein meets John Cage meets Matthew Barney, which I think I will take as a compliment. So people sometimes ask me, though, why cinema and particle physics? What do those two things have in common? Why are they both in your brain at the same time? And for a long time, I couldn't articulate it, to be honest. I would typically say something like, they both require creative thinking, or they're different and complementary ways of viewing the world, but only in the past few years, after I created this X-Noise project as an attempt to connect on a more visceral level with my artist friends in particle physics, about particle physics, and after I've interacted with more artists who passed through CERN, and after I've participated in various projects that involve collaborations between artists and scientists, only recently have I come to a better understanding of why these two things have obsessed me for so long. Because I'm honestly neither a physicist nor a filmmaker, although those names are useful shorthand. Particle physicist is shorthand for ravenously curious little kid who could never accept that's just the way it is as an answer. It's shorthand for person who is inexorably drawn to figuring out how things work. I've always been naturally obsessed with understanding the underlying rules, the hidden structures around us that lead to or govern the world we experience. And both particle physics and cinema and art in general are methods of exploring the world around us to expose and understand and access the hidden structures behind everything we experience. There's a moment in Louise Buñuel's 1970 film, Tristana, where the main character is visiting a church. She pauses, she leans down and hovers for a moment over a marble statue of a reclining priest. Buñuel, who'd spent his entire life and career objecting to oppressive regimes and to dedicated to exposing the hypocrisies of powerful people and institutions, in this image allows Catherine Deneuve's Tristana a shocking moment of clarity. Tristana is positioned above this ostentatious symbol of thousands of years of the structural subjugation of women, and she seems to briefly enjoy this position of power. But the pleasure is tempered by the simultaneously recognition that this is likely the only way she'll ever have this power, superficially, over a man immobilized in marble. And I chose a different image from Kelly Reichardt's 2010 film, Meek's Cut Off, than the one that I want, which is at the end, and if you've not seen it, I don't want to spoil it for you, but the film explores what forces, some subtle, some overt, compel people to do drastic things in difficult situations. The forces at play may be completely superficial, or they could be hiding in emotional realms we won't or can't acknowledge. And my favorite collaborations between art and science are those that, because of the collision of two minds from different disciplines devoted to uncovering hidden spaces and understanding the structures and rules therein, the collision of these creative minds creates a completely novel space. Much like a proton collision can potentially coax a hyperdimensional graviton into existence briefly in the Large Hadron Collider, briefly accessing extra dimensions of space, extra structure. This creative collision creates a novel space where new ideas can flood in and from which new artistic concepts can emerge. And there's a hidden dimension here, too, a hidden structure, an addendum to that shorthand description of myself as a particle physicist, which is the following. Ravenously curious little kid who could never accept that's just the way it is as an answer, and somehow found himself in the right socioeconomic situation to be able to pursue particle physics in a supportive, benevolently challenging environment to complete a PhD and work at the largest, most prominent particle physics laboratory in the world. There's a lot of caveats there that we don't always acknowledge. My loves of science and art were nurtured and supported largely due to where I happened to have been born. Other kids weren't so lucky. So my goal is always to find ways to not just communicate science or engage with the public, language that, although I sometimes use, really does reinforce an artificial barrier based upon the prestige and status of big science. And as a side note, I'd just like to point out that we should abolish the Nobel Prize for many reasons, or give knowledge to the world, but instead to construct a world where the line between scientist and non-scientist dissolves. And we're just left with a huge, passionate, hyper-inquisitive group of humans, each of which contributes to our ability to explore the world, to achieve discoveries, to extract new knowledge and make reliable empirical conclusions about the universe that everyone can appreciate and that everyone is a part of, because every human, in a very real sense, is involved in scientific inquiry. And I'll use the example of the Large Hadron Collider. It's not just me and my physicist colleagues, though them too. Not just the engineers and technicians and support staff, though them too. Not just the facilities and civil engineers in Switzerland and France, though them too. And not just the administrators at all the universities around the world who support the scientists who work directly on the LHC and the people that gave them coffee when they went in the morning, though all of those people too. All of those people own a part of the Higgs boson discovery, period. There's currently a huge privilege associated to being able to study science at its highest echelons and to be able to call oneself a scientist. But this distinction is far sharper in the social mindset than it needs to be, and is likely doing this disservice to the entirety of the scientific pursuit. Acknowledging it is just the first step. And unfortunately, few people around the world are lucky enough to be able to respond to that's just the way it is by going to a library or by going to college. But even so, when I give talks, I get asked to give advice to students, and my answer applies universally to all citizens, to scientists, to politicians, and to artists. look where no one else is looking. Explore realms that no one else is exploring. Don't accept that's just the way it is as an answer, ever. Look where no one else is looking in science, in politics, and art, because if you do, you may discover absolutely revolutionary things. You may discover extra dimensions of space. Extra dimensions of space, that's amazing! To explain the bizarre mystery of why gravity is so weak. You may discover what 95% of the universe is made of, or if instead we need to radically alter our view of the cosmos to allow for the possibility that our world is a hologram. You may discover a way to innovate the technology needed to build a particle collider around the circumference of the moon to help us better understand if we might live in a multiverse. You may also discover why, in our universe, women and persons of color are so persistently underrepresented in physics and math. And not just discover why, because we already know many reasons why, but discover an effective method of addressing and correcting the problem, not only so that science will benefit from the missing voices and perspectives in our endeavor, but also simply because the opportunity to participate fully in the joy and wonder of scientific inquiry should be available to every human being, because the joy of scientific inquiry should be a human right. Look where no one else is looking. We need you to do this, to uncover even more complex, rich, fascinating, and sometimes oppressive structures behind everything around us. Because only by doing so will we better understand how to construct a world where everyone is afforded dignity, respect, equality, equity, opportunity, and love. Science can help achieve this technologically and intellectually. Politics is intended to help achieve this practically and socially. And art can help achieve this by holding up a mirror to the way that we organize and conduct ourselves in societies, to better understand the emotional and psychological structures inside ourselves. Look where no one else is looking. Uncover the structures behind it all, because whatever labels, excuse me, because whatever labels or names you put on them, art and science are fundamentally similar pursuits. Each is an attempt to discover the underlying rules, structures, and messages of the world around us. Messages and rules that often seem so hidden as to be encrypted. Each is an attempt to better understand our place in the universe. That is why I am humbled to speak to this particular crowd. You, because you are the people doing this hard work every day interfacing with budding scientists and people who have forgotten that they are still secretly scientists. And people, keep going, don't stop. Particle physics is definitely on the cusp of a revolution. And society seems to be, but together, you, scientists, communicators, science communicators, designers, artists, makers, together you are doing the hard work to slowly unravel the hidden structures preventing us from already having a more equitable, sane world. And you are constructing a better universe. Because you know what? The person who finally discovers dark matter, or supersymmetry, or formulates a new way to test whether we live in a multiverse, or fixes wealth inequality, or succeeds in providing free healthcare to all citizens, or composes a hip-hop album that resonates with millions of people, this person is probably walking through the doors of a museum, maybe a science museum. Maybe she's coming in with a group of loud, boisterous students, and she struggles to be heard over them. Maybe she can't see past the crowd to play with the exhibit with the air tube and the beach ball that everyone else wants to play with. Maybe she wanders away from the other kids and sits down at a different exhibit about magnetism. She sees a little handle at the edge of the table. She grabs it, pulls it up, and a panel opens, revealing a bunch of extra magnets that she can play with. She closes the door because she's not sure if she's supposed to look in there. She's by herself. all of her other friends yelling in the distance, and she looks around. And you here in this room, you are the most important people in the world, because you are the ones who can walk to her, bend down, and remind her, yes, keep going. Look where no one else is looking. Thank you.